Hello everybody, my name is Zelinka, I'm from VSB Technical University in Austria, and in fact I'm kind of alien on this conference because I'm not astrophysicist, even not astronomer. However, because astronomy was my hobby since my childhood and stay forever, I try to combine it with my profession. And the last 3 years we had some research ground with boys from Charles University and Astronomical Department, where we try to combine artificial intelligence and some data from robotic telescopes. So that's me. Yeah. Okay, so I will maybe use this one, that's better. I come from this university, which is located on the north part, northeast of Czech Republic. Everybody of you know that. I'm head of the research group, which is called NAVY. This is Czech abbreviation of the Unconventional Computational Algorithms, and our research is focused on many kind of areas from computer science. And today I will talk about using those methods on the Astroinformatic data. This presentation consists of 2 parts. In the first part, I must introduce to you some algorithms which are called evolutionary algorithms, and in the second part, I try to explain you how we use them on those astrophysical data. However, if you are familiar with evolutionary computation, let me know and I can overstep it. So, briefly, what is it, evolutionary algorithms or evolutionary computation or bio-inspired computation? That's part of computer science which is based on the Darwinian theory of evolution and Mendelian theory of heritage. I very often use those pictures because usually abroad everybody say Darwinian theory of evolution, Darwinian theory of evolution, but everybody forget that the same research in the same time has been done by Gregor Johann Mendel here in Brno. And while Darwin described his theory from the macro point of view, that means from the macro level, he observed species and so on, as you know. Then Gregor Mendel did research on the, say, genetic level, because he tried to combine some vegetables and try to derive the mathematical description of the transformation of information from generations to generations. So these 2 men contribute to the evolutionary theory, which has been then used by Alan Turing, who defined first ideas about evolutionary computation. He used terminology which is used today, and after him, Barry Cherry from the Princeton made in the 50s first numerical experiments, and after Barry Cherry, modern evolutionary computer scientists follow him. Today, when you open literature, you can see that John Holland was the first who proposed genetic algorithms. Well, this is not true, because the ideas come from Turing and first experiment from the Barry Cherry. And what does it mean, evolutionary algorithm? Basically, try to imagine that you have a model. You develop some model which has n unknown variables, 1, 2, 5, 1 million, doesn't matter. And those variables should be somehow estimated by trial-error procedure or Gaussian method or whatever else. So, evolutionary algorithms work in such a way that they work with so-called population. This population consists of individuals. Individuals are vectors of those unknown variables which must be estimated. And this population is somehow evaluated for fitness. Each individual, each vector of actually set parameters is evaluated for its quality with the comparison with some data or model. And its quality called fitness then say who of those individuals, now called parents, is selected for creation of the offsprings. So we define somehow problem, select possible solutions in a random way on the beginning, then evaluate fitness and select parents for the creation of offspring. Offspring are created. Each algorithm has a different way how to do it, so it's nonsense to talk about some specific process. When offsprings are created, that means new combination of the vectors appears. They must be mutated because the mutation is a very important part of those algorithms. Without mutation, we would be only limited by combinatorial limits, while mutation push us away beyond the combinatorial possibility, and again evaluated for fitness. So in this moment we have a new offsprings which we know with new fitness, and then comes to the role selection of the best individuals from whole population, from the parents and offsprings, and only better survive. So after this loop, is created new population with the best solutions which has been found during this loop, and the worst are thrown away, simply died out or wiped out. That loop is called generation, as in normal nature. Now you can see that in this loop we somehow proceed information, get new solutions, and after this loop we have slightly better solutions. And when we repeat those generations once again, then you can see that somehow statistically slightly better solutions till we reach some very good solutions which are usually very excellent and very acceptable. There's some video of one of the swarm algorithms, because the evolution algorithms are a wide class of algorithms, and during last 10 years appears so-called swarm intelligence algorithms, which is in fact in many attributes similar to classical evolutionary algorithms. And that video basically demonstrates ideas I described. So we have some surface of possible solutions. Global minimum is here. We are looking for global minimum. That means for setting of our parameters of our model so that its behavior will fit observed data as much as possible. Tooth difference is minimal, and that means the lowest point on that surface of possible solutions. Though individuals are randomly selected over the surface of possible solutions, and now they will be evaluated for their fitness. The higher temperature, higher blue bar means better fitness. I apologize for these funny faces. It was done by my students in the frame of this bachelor thesis, but I found that people usually like it on conferences, so I'm using this. The swarm intelligence works so that there is usually selected one of the best solutions, like leader or main particle in the case of particle swarm, and so on and so on. And then mutual interactions among those individuals in the populations somehow reorganize this swarm or this population so that they travel through that series of possible solutions in kind of random deterministic way, and as you will see, are able to overcome local optimas and find finally some locus optima, which is here. So I let it run. It's only 4 minutes video. Meanwhile, I try to speak freely. So that's a swarm intelligence algorithm. So we have today a class of classical evolutionary algorithms, for example, genetic algorithms, or another one, then algorithms which somehow mimic the physical processes like metallurgy. Typical example is simulated annealing, or partly stochastic like hill climbing algorithms, or classical algorithms, today classical like differential evolution, which is very powerful, and so on. Now you can see that this individual, based on some mutual interactions and his traveling through the path of this search of possible solutions, has been trapped in the local optima. So you can say, okay, that method doesn't work, but this is not true, because he's waiting for next generation interactions with another individuals, and as we will see, it will pull him up from this minimum, and whole population will then converge to the global minimum. Those algorithms has one big disadvantage. They are partly stochastic. Randomness play a role in mutations, so just there is no possibility to create mathematical proof which say it converges all the time everywhere. You can just say that it converges with higher probability or something like that. However, when we work with such algorithms, we don't use only one simulation. We use it many times, and then somehow statistically proceed to the results, and based on the results we can say that we are with very high probability in some global extreme, or we found some suitable solution. And believe me, it works. We have used those algorithms, for example, in Plasma Laboratory, Oxford, 10 years ago, and in real time those algorithms has been able to control plasma reactor without any mathematical model. There was so many combinations that if we would use brute force approach, that means evaluate all possible control inputs to that reactor, it would take, try to guess how much? 10 powered by 42 years. Evolutions found solutions during 4 minutes. In the case of repeated simulations, the same solution during 4 minutes. So those algorithms are really very powerful, and even Boeing used them to optimize the thrust power of the engines in Boeing airplanes, and so on and so on. We use those algorithms also to optimize the aircraft wings for the LED Kunovice and many other applications. So now you can see the fairy tale is going to the end. Everybody is happy and going to the global extreme. And as you will see, this one tried to now attract another individuals. Because of the jumping and overjumping, they very soon come to the global extreme. when I was young, I'm still young, but when I was a bit younger, and then 20 years ago, when I was PhD, I tried to propose these ideas to mathematical conference somewhere in the deep forest in Czech Republic. I talk about it, and those algorithms that time were not so well known in this country. And I was very enthusiastic, and I was talking about it. And I saw in the audience one older professor who was red, white. I said, oh, well, there is some problem. And then he stood up in the discussion and said, it's not true, those algorithms cannot work because there is no mathematical proof. But nature don't care about our opinion and proofs, you know, this is based on the nature principles. So, that was the video. Let's go further. That's another animation how time development of the population on some test functions. Today the community has a very huge set of benchmark test functions which very easily and nicely can test whether those algorithms are really powerful or not and working or not. So believe me, they are really very well working. Also the classification of those algorithms is various. There are different algorithms and their classes overlap themselves, so it's very hard to say that this algorithm is purely evolutionary and so on. I'm sorry for the speed, but this topic I use only for one semester, so it's nonsense to tell you everything during half an hour. This slide is here only to show that, of course, we are limited by nature, and there is a lot of kind of limits for computation, like physical limits from quantum theory, thermodynamics, or complexity theory. And those algorithms are very useful in that cases because they overcome classical algorithms and all those levels of limitation are able to deliver very good engineering results. Most popular last time are swarm intelligence algorithms like particle swarm. Very nice and very special idea which I propose on conferences is that my very favorite Polish science fiction writer, Stanisław Lem, he wrote many nice books and he predicted swarm intelligence and swarm robotics in the 60s. So we discovered and started to talk about it 10 years ago and he discovered that in the 60s, which is fantastic. So this idea is quite old in the case of the science. Okay, let's go further. Why I'm talking about it? Because that was just preliminary information. Evolutionary algorithms in general are numerical algorithms to estimate numerical parameters. However, they can be used also to build up the models, mathematical models on data, which is part of today's presentation, so that those models can describe behavior of the robot or design the antenna. That antenna has been developed by genetic algorithms for NASA competition. NASA announced competition for some antenna for space probe, and many people try to propose their design, usually recognize symmetric and so on, and then somebody used genetic algorithms, and there is a result. It looks like design from a madhouse, but the emission, I don't know how to say in English, characteristics of this antenna won the competition. I don't know if NASA used that. However, that's the winner of the competition. There are today another versions of evolutionary computation called symbolic regressions, and usually genetic programming, grammatical evolution, and analytic programming. We have used analytical programming, which allow us to build up from the basic building block elements the higher structures. So while classical evolutionary algorithms estimate numerical parameters of your model, that way, that superstructure, or how to say in English, nástavba, of the evolutionary computation, allow to handle with non-numerical objects, like mathematical symbols, formulas, and so on. Here I am using for demonstration just electronic elements, and symbolic regression driven by evolution can build up structure like amplifier, for example. It has been proved and already patented. This is a result from our previous experiments when we try to synthesize the control commands for this robot so that it passes through whole path without any leaving. And the program is here. It is not written by human. It is synthesized by evolution. There are only basic building block elements like move to the right, move to the left, turn, and so on. And evolution combined them in the principles I described in the beginning, and those structures, when they grow up, start to work like programs. So it's designed fully by computer, not by humans. That's the principle of the symbolic regression. Basically, each formula, mathematical formula, or any kind of description, even linguistic formula, can be described in the form of the trees. And if you take a look on those trees like on parents, and crossover creating the offsprings is taken like cutting of those branches and exchange of them, then we get totally different formulas, totally different trees, plus mutation and so on. So that's the main idea of symbolic regression. And we use those ideas on those astrophysical data. Again, sorry, I'm not astrophysicist. I can just talk how we get information from our colleagues. And those data has been taken from the Ondřejov Astronomical Institute, from our friends. It contains about 1,500 sample data, and those data sets has been artificially manually divided into so many samples and classes. So we had 4 classes we will see on the next slide. And each this spectra curve had consists of so many equidistant points. Then we of course made some normalization and purification of those data. Basically these 4 classes should be like this. This is pure emission, some emission with small absorption part, pure absorption, and let's balance absorption and emission. So we try to use analytic programming to synthesize a mathematical description of those spectra, to use them to classify those huge data from those telescopes. Because today there are robotic telescopes, it is estimated that during one night one robotic telescope produced about 1 petabyte of data. I read somewhere that Kepler used the need for discovery of the planetary motion law only 400 kilobytes. So 400 kilobytes and 1 petabyte. Can you imagine how much information we miss if we don't process it all? So that was the reason why we tried to do those very simple experiments. We of course made some normalization and denoising. We tried to pick up and prepare those spectra so that we move them to the origin, take only some points around the origin, and the rest of the spectra, which was not important for classification, we throw away, taken as a noise. And then we try to synthesize some formulas which has been used for classification. This is just demonstration of how were calculated average representatives of each class, and how was done evaluation of the actual spectra, and some formula which represents different class. And difference between those two curves were taken like fitness of the individual, that means of the mathematical description of that spectra model. Together with our approach has been used classical classificator like random decision forest, as support vector machine, and other very well accepted methods in computer science. There is one another extension. Normally for mutation in individuals in evolution we used classical random number generators. In this case we use chaotic systems for reasons which I can explain easily, but there is no time. We used about, I don't know how much will be on the next slide. Here, so many chaotic systems instead of random number generators, because we found in the past that those generators, evolution with those generators work very well, better than with random number generators. But why, it's beyond discussion of this presentation. We used for experiments analytical programming and SOMA algorithm, which you already saw on the video. And the basic building block elements for the analytical programming were only this one. Plus, minus, times, divided, x and k. K is general constant and x is unknown variable. And the parameter of the evolution has been said like this. I was talking about those chaotic generators. Computational conditions were like this. We used for experiments our supercomputer in Ostrava and make it on the MPI software. So we used such kind of technology. First time we tried to use on single computer, it took about 36 hours, while on the supercomputer it took only 30 minutes. In C# or C++, I think. And the results, this is only a shortcut from the results. This table shows how many classes, which class, how many times has been correctly classified and with what kind of percent success. And this is part of our experiments. In fact, this table, end of this table is somewhere down there on the floor. This is a long table in the journal paper. So we used together one algorithm, however, many different chaotic systems to prepare the mutation inferior algorithms compared with those classical methods, and we found that in many cases we are the same or slightly better. So, as a conclusion of this presentation, I would like to say that we use evolutionary technology enriched by strange non-chaotic attractors as well as with chaotic attractors. We try to use some spectra of DE stars, which has been delivered by our colleagues from the Ondřejov, together with our colleague from Charles University. As a symbolic regression, we have used analytical programming, and altogether it has been used for classification, which seems to be successful, and it has been published in this paper after 2 or 3 rounds of review. So that's the main idea of my presentation. I apologize for my Chinglish, that means Czech English. And if you have any questions, please don't hesitate, because I must leave around 7 o'clock and you never see me anymore here today, even tomorrow. But anyway, after that I can be here again, or we can talk with via emails. Thank you very much, and I hope that I did.
Perfect time.
Oh, very quick. Thank you.